Monitoring and analyzing vibration is an important part of maintenance on any rotating equipment. That's because all rotating equipment vibrates, from this small electric motor to this complex turbine generator. And each part within the rotating equipment also vibrates. Measuring and then analyzing this vibration can help you to determine the operating condition of your equipment. That's because vibration patterns change as equipment wears. Vibration is simply motion, movement back and forth or up and down. As the operating condition of the equipment changes, the associated vibration can change in direction, and it can change in amount. For example, as a bearing wears, you should expect the amount of vibration to increase. This is a normal occurrence when the machine's rotating parts start to wear. By monitoring the amount of vibration over time, you could determine when the bearing would need to be replaced. The amount of vibration is called the amplitude. Vibration amplitude is a measure of the severity of vibration. The greater the amplitude, the more severe the vibration. Two commonly used measures of vibration amplitude are displacement and velocity. Displacement refers to how far the part moves from its rest position at the center of rotation. Velocity refers to the speed of vibration. Let's use this drawing of a shaft to see more about these measures of vibration. In order to illustrate more clearly, we'll exaggerate the movement of the shaft in the housing. As the shaft rotates, it is displaced or moved from its rest position. First it moves in one direction, then in the opposite direction. This movement from the rest position is the displacement. Displacement can also be illustrated using a sine wave. On this sine wave, the center line represents the shaft's position at rest. The sine wave shows the displacement of the shaft first in one direction and then in the opposite direction as it completes a rotation. Here, it has returned to its rest position. Total displacement is the distance the shaft travels from its rest position during one revolution. So, total displacement is represented by the distance from one peak of the wave to the next peak. This peak-to-peak displacement is measured in mils. 1 mil is 1/1000th of an inch. So displacement, measured in mils, is one way to determine the severity of vibration. The other measure of vibration is velocity. Velocity can also be illustrated using a sine wave. The velocity of the shaft is zero when displacement is at its peak in any direction. This is because the shaft must stop before it can start to move in the other direction. So velocity reaches its peak where displacement is zero, here at the midpoint of the cycle. This is where velocity is measured. Velocity is measured in inches per second. Now that you understand the basic concepts of displacement and velocity as they refer to vibration, let's see how they're related. We'll use these simplified drawings to illustrate certain points during one revolution of a shaft inside its bearing. Here, the shaft is at the center of its rotation. Displacement is zero, so velocity is at its peak. Here, however, the shaft has reached the limit of its travel. It must stop before moving in the opposite direction. So velocity is at zero, displacement is maximum. It's important to understand displacement and velocity, since you'll be using these measurements in monitoring and analyzing vibration. The equipment you'll be using to measure vibration amplitude and the procedures you'll follow are designed to fit the particular needs of the rotating equipment in your facility. So it's important to follow your facility procedures carefully. It's good practice to record your readings as you take them. And whenever possible, you should take 3 different readings at each measurement point: a horizontal reading, a vertical reading, and an axial reading. The horizontal and vertical readings are called radial readings because they measure the vibrations traveling outward on a radius from the shaft. Axial readings, on the other hand, measure the vibration traveling along the length of the shaft. Let's look at an example. The shaft illustrated here passes through several bearings. To get the most complete picture of machine condition, you should take both horizontal and vertical radial readings at each bearing. And on any bearing where it's possible, you should also take an axial reading. In this case, the only bearing accessible for an axial reading is the one at the end of the shaft. So in order to measure the severity of vibration, you'll measure displacement or velocity at several places along a shaft. Then you'll need to compare your measurements to specifications for that machine. In the next segment, we'll see how to evaluate your vibration measurements. But for now, stop and review the information on monitoring equipment vibration that you've seen here. Information about the operating condition of the equipment. One way to evaluate vibration readings is to use a severity chart. This shows a typical severity chart. It's been simplified somewhat so that you can read it more clearly. You'll notice that each side of the chart is marked with information. The top and right-hand sides of the chart are marked in mils. You'll recall that mils are used to measure peak-to-peak displacement. The bottom of the chart is marked in revolutions per minute, or RPM. This axis represents the speed of the operating equipment. The left-hand side of the chart is marked with two scales. One is inches per second, representing a vibration velocity reading. The other scale is the severity scale. You'll notice that it's divided into categories representing operating states of the equipment. These categories range from smooth operation, which would be typical of new equipment, to very rough operation, which would be an indication that the equipment is in danger of breakdown. To use a severity chart, you find the axis with the vibration reading you've taken, for example, inches per second or mils. Locate the specific reading along the appropriate axis. Then find the operating speed of the equipment along the bottom axis. Follow the lines for the vibration reading and the equipment operating speed until they intersect. Then follow across to the corresponding category of severity. For example, let's say that you've obtained a vibration reading of 0.2 inches per second, and the equipment is operating at 1800 RPM. Follow the line from the inches per second reading until you come to the intersection with the line for 1800 RPM. Then follow straight across from the intersection to determine the level of severity on the left side of the chart. In this case, the level of severity would be categorized as fair. Let's look at another example, this time where the vibration reading is in mils. Let's say, for example, that the measured displacement is 1 mil, and the speed of the equipment is 8,000 RPM. Following these two lines to their intersection brings us here. Then, following this line of intersection across to the left, we can determine that the level of severity is here. This indicates that the rotating part is operating in the rough range. This is a sign of a severe problem. So, a severity chart is a first step in evaluating the vibration readings you obtain. A severity chart can be used to determine the operating condition of equipment based on vibration readings. However, a severity chart cannot help you determine the cause of the problem. In order to determine the cause of a vibration problem, you have to analyze the vibration. In the next segment, we'll see how to use a vibration analyzer. But for now, stop and review the material you've seen here. Last segment, you saw how a severity chart can be used to determine the operating condition of equipment based on vibration readings. In this segment, we'll begin to see how to use vibration analysis to determine the cause of the vibration problem. Vibration analysis is a method of interpreting vibration readings taken on rotating equipment. What does this involve? The first step in determining the cause of the vibration is to identify the frequency at which it's occurring. Frequency is simply the number of cycles in a given period of time. In vibration analysis, frequency is commonly measured in cycles per minute, or CPM. As you might suspect, the frequency of vibration measured in CPM is related to the rotating speed of the part, measured in RPM. The frequency of vibration will usually be a multiple of machine RPM. Every rotating part will produce a certain level of vibration that's characteristic of that part, and every machine fault, misalignment, unbalance, and so on, will also produce a characteristic vibration. Monitoring vibration amplitude can alert you to the presence and severity of a problem. Analyzing vibration frequency gives you the basis for determining the cause of the problem. A vibration meter can only measure the amount or amplitude of the vibration. But the basic function of a vibration analyzer is to pinpoint the frequencies at which high vibration amplitudes occur. Remember, This is the first step in determining the cause of excessive vibration. Since analyzers and procedures can vary, it's important to follow the manufacturer's instructions for the equipment used at your facility. Let's look at this vibration analyzer to find out what kind of information it can provide. This analyzer can provide both unfiltered and filtered readings. The filter out setting on an analyzer is the unfiltered setting. It measures all vibration and gives you an overall picture of vibration severity. The filter on a vibration analyzer filters out all but a specified range of frequencies. Naturally enough, the sharp filter has a narrower range of frequencies than the broad filter. The broad filter function on the analyzer allows you to scan through each filter range until you find the frequencies or peak amplitude. Then you can use the sharp filter function to tune in on these frequencies. In this way, you can get the most precise readings possible. These readings are the ones you need to pinpoint the source of a problem in your machinery. You can check that you've located all the significant frequencies by comparing the filter out vibration amplitude with the sum of the filtered vibration amplitudes. If you've located all the significant frequencies, the two totals should be the same. For instance, say you had a filter out reading of 0.5 inches per second, and your first filtered reading was 0.3 inches per second. Since the sum of your filtered readings should be equal to or greater than the filter out, you need to keep scanning through the frequency ranges until you locate all the vibration. Many vibration analyzers record amplitude and frequency in the form of a vibration signature. A vibration signature gives you a visual picture of vibration amplitudes at particular frequencies. As you know, when it's possible, readings are taken from three directions. You can compare the vibration amplitude on the horizontal, vertical, and axial signatures. This will help in determining the condition of your machinery. Let's look at an example to see how you would analyze a vibration signature. This vibration signature was taken from a machine operating at 1800 RPM. One of the first things to look for is where the peak amplitude occurs in relation to the equipment RPM. As you can see, here the peak amplitude, measured in CPM, occurs at 3600 RPM. When you compare the frequency of vibration in CPM to the equipment's operating speed in RPM, you can see whether any pattern is evident. Here, the peak amplitude occurs at 2 times the operating speed of the equipment, so the equipment is said to have a vibration multiple of 2. Different vibration multiples can indicate different causes of vibration. In the next segment, we'll see more about the ways you can interpret vibration signatures to determine the cause of vibration. But for now, stop and review what we've seen here. This is a practical and efficient tool for troubleshooting problems with rotating equipment. The data you collect, the amplitude and direction of vibration and its frequency, give you valuable information about a machine's condition. When you put this information together with your working knowledge of particular machinery, you can find the most probable cause of excessive vibration. In this segment, we'll start to look at some common problems found on rotating equipment and how they'll show up in a vibration analysis. Let's begin with a rotating part that's out of balance. While no rotating part is perfectly balanced, machine unbalance is a common cause of excessive vibration. The unbalanced shaft from which this signature was taken rotates at 3600 RPM. Since the shaft RPM is 3600 RPM and the peak amplitude occurs at 3600 CPM, this is a multiple of 1 times the RPM. This multiple of 1 times RPM is a common pattern for unbalance. To see why this is so, let's take a closer look at the condition of unbalance. Unbalance simply means that the part's rotational center is not the same as its physical center. This is exactly like an unbalanced tire. Each time an unbalanced tire rotates, the heavy spot vibrates when it makes contact with the road. As an unbalanced shaft rotates, the vibration produced by the heavy side is picked up as it passes the probe, 1 time every revolution. However, unbalance is not the only problem which can cause vibration at a frequency equal to 1 times RPM, as we'll see in a few moments. Other clues may help you pinpoint the problem. For example, the direction of vibration is a clue as to the cause of vibration. So you can compare the readings taken from the radial and axial positions. As you can see, the vibration produced by unbalance is primarily radial in direction, measured either horizontally or vertically. That's because the center of the shaft's rotation has shifted to the side, and the vibration will travel outwards from the heavy side of the shaft in the radial directions. So vibration amplitudes at 1 times the RPM in the radial directions are a good indication of unbalance. Since no rotating part is ever perfectly balanced, you'll usually see some vibration due to unbalance at 1 times RPM. The amplitude of the vibration will be your guide as to the severity of the problem. Another shaft-related problem that will cause vibration is misalignment. Let's see what vibration characteristics might indicate misalignment. There are 2 basic types of misalignment: offset misalignment and angular misalignment. Although the 2 most often occur together, let's look at the characteristics of each type of misalignment separately first. We'll start with offset misalignment. In offset misalignment, the center lines of the 2 shafts are parallel to each other, but are not lined up. So, although they are rotating together, one shaft is being forced in one direction, while the other shaft is being forced in the opposite direction. The vibration produced by this condition will reflect both these forces. This is a simplified drawing of the signature produced by offset misalignment. Each rotation will produce a vibration at 2 times the shaft's RPM. The vibration produced by offset misalignment occurs primarily in the radial direction. The amplitude of vibration is a good indication of the severity of the misalignment. What about angular misalignment? What are its primary characteristics? In the case of angular misalignment, 2 shafts are at an angle to each other. Vibration produced by angular misalignment would usually occur at a frequency equal to the shaft's RPM. In the case of angular misalignment, only one force is operating on the shafts. This force will be picked up by the analyzer's probe at the shaft's bearing. You'll recall that unbalance also occurs at 1 times shaft RPM. To determine whether the problem is caused by unbalance or misalignment, you need to look at the direction of vibration. For example, vibration produced by angular misalignment will be indicated by vibration amplitudes both radially and axially. That's because vibration travels outward from the shaft's coupling. But because the shafts are rotating at an angle to each other, vibration also travels down the length of the 2 shafts, causing axial vibration. Unbalance, on the other hand, is primarily radial. These 2 types of misalignment problems, angular and offset, can exist together. In fact, this is much more common than finding angular or offset misalignment alone. So, the presence of both radial and axial vibration is an indication that misalignment may be the problem when high amplitudes of vibration show up at both 1 and 2 times RPM. Usually, the amplitude at 1 times RPM will be higher because angular misalignment tends to be more severe. But you'll need to use your practical experience of individual pieces of machinery because more than one kind of machine problem can produce similar kinds of vibration. In the next segment, we'll continue to discuss various vibration signatures of other common machine faults. But for now, stop and review what we've seen here. In the last segment, we looked at some shaft-related problems that can be detected through vibration analysis. In this segment, we'll continue to look at some other problems common to rotating equipment and see how they show up in a vibration signature. One very common fault in any kind of machinery is mechanical looseness. In rotating equipment, mechanical looseness simply allows another kind of machine condition to show up. For example, any residual unbalance would be intensified by mechanical looseness. This vibration signature was taken on a bearing with a loose housing. The machine RPM is 1800. As you can see, there are 2 amplitude peaks. One occurs at 1800 CPM, or 1 times RPM. The other peak amplitude occurs at 3600 CPM, or 2 times RPM. To see why mechanical looseness produces vibration at both 1 and 2 times RPM, let's look at this simplified picture of an unbalanced rotating part. The amount of unbalance might be acceptable in itself, but it's aggravated by the mechanical looseness. This bearing's housing is loose, so with every revolution it's pulled upwards to the extent of the mechanical looseness by the rotational force of the shaft. Then, as the heavy spot rotates downwards, the bearing falls down to the base, again causing vibration. So every revolution generates two forces, which will show up at 1 and 2 times RPM. As you would expect, the amplitude of the vibration will increase as the amount of looseness increases, and the amplitude at 2 times RPM will usually be greater than at 1 times RPM. This is because as the bearing rotates downward, it moves at a greater velocity through its rest position. This higher velocity is due to the gravitational pull on the heavy spot and the rotational force of the shaft within the bearing. Since mechanical looseness allows any residual unbalance to show up, the vibration caused by this condition will be primarily radial in direction. The peak amplitudes will occur in the radial directions, here vertically. You can usually distinguish between mechanical looseness and other machine problems because of the higher amplitude at 2 times RPM in the vertical direction. But, as always, you need to consider the design and operation of individual machines in order to fully apply the data from vibration analysis. For example, the patterns of vibration that show up in relation to gears are quite different. The vibration caused by worn gears will occur at a frequency that's a high multiple of RPM. Let's see why. The frequency of the vibration is dependent on the number of gear teeth. Vibration caused by worn gears occurs at what's known as the meshing frequency because of the meshing of the gear teeth on 2 cogs. The meshing frequency is equal to the number of gear teeth times RPM. For example, if there are 75 teeth at 2,000 RPM, the meshing frequency would be 150,000 CPM. So, vibration occurring at a very high frequency could be related to gears. Now let's look at another kind of machine component that causes high-frequency vibration: anti-friction bearings. The number of rolling elements in an anti-friction bearing affects the frequency of vibration. So, as anti-friction bearings wear, you'll typically see vibration amplitudes at high frequencies. These signatures can be distinguished from other types of vibration in 2 ways. The vibration amplitude tends to be fairly broad and doesn't usually occur at an exact multiple of RPM. This is due to the nature of the construction of rolling element bearings. Since the inner race is smaller than the outer race, the frequency of vibration is different at the 2 races. A general rule of thumb for determining frequency is the number of rolling elements times the RPM times 45% for the outer race and times 65% for the inner race. But since the rolling elements are in contact with both races, the frequencies occur over a band of frequencies. Again, experience with familiar equipment will help you recognize particular vibration patterns. A good working knowledge of your machinery is an important source of information. Vibration analysis can provide you with valuable information for troubleshooting and maintaining rotating equipment. It can help you concentrate on the probable causes of excessive vibration and eliminate the unlikely possibilities. The key to using vibration analysis as an effective maintenance tool is your ability to relate vibration information to particular machine problems. This training program has been general in nature. When operating and working on any equipment in your plant, be sure to follow the procedures provided by your facility and the equipment manufacturer. If you have any further questions, talk to your supervisor, and always use the best safety practices when doing any work.